Welcome to another video of Optatube. Today, we're going to dive into the hidden brain of our power grid.
Just think about that for a second. Every single time you flip a switch, somewhere out there, a power plant has to generate that exact amount of electricity, and it has to do it instantly. But you've got dozens of plants to choose from. Some are burning cheap natural gas, others might be older and less efficient, and they all have different costs. So how does the system decide which ones to ramp up or down to give us reliable power without, breaking the bank? What you have is this massive real-time optimization puzzle happening constantly.
And it turns out that puzzle actually has a name. It's called economic dispatch. It's this really elegant mathematical process that grid operators use every single second of every single day to solve this exact problem. So let's break down how it really works.
All right, first things first. In any optimization problem, you have to have a crystal clear goal. And for economic dispatch, the objective is, well, it's beautifully simple.
I mean, it really is as simple as that. We are on a mission to find the absolute cheapest way to generate the power we need across the entire system. That's it. This one idea is the guiding principle for everything else that follows.
Okay, so to minimize cost, we first need a way to, calculate it, right? And this is where the quadratic cost function comes in. Now, I know it looks a little intimidating, but trust me, this is the workhorse formula that models the real-world cost of running a single power plant. Let's break it down piece by piece.
The key thing to get here is that every single part of this formula stands for a real-world cost. P is just how much power you're making. That A term, that's your fixed cost. Think of it as the cost just to turn the lights on at the plant itself. The B term is your variable cost, which is mostly fuel, and it goes up the more power you generate. And what's really cool is the C term. It represents the fact that as you push a generator closer to its max limit, it actually gets less efficient, so the cost per megawatt starts to climb faster. This one little formula does a brilliant job of capturing that physical reality.
Okay, so we have our objective, minimize that cost function. But, we can't just do whatever we want. We've got to play by the rules of the physical grid. And in the world of optimization, we call these constraints.
And for this classic economic dispatch problem, there are two rules you absolutely cannot break. First, power balance. You have to generate exactly as much electricity as people are using. No more, no less. And second, generator limits. Every power plant has physical limits. It can't produce infinite power, and often it can't be turned down to zero without shutting off completely.
So let's look at that first rule. The math here is just a fancy way of saying that the sum of all the power from your generators, minus what all the customers are using, has to equal zero. It's got to be a perfect balancing act.
And this visual, it just makes it so clear. If the total demand from everyone is, say, 150 megawatts, then the output from generator 1 plus generator 2 plus generator 3 must add up to exactly 150 megawatts. Our whole job is to figure out the exact height for each of those bars that hits that demand line, but does it at the lowest possible total cost.
And rule number 2 is just as critical. Each generator's power output, that P value, has to be somewhere between its minimum safe operating level and its absolute maximum capacity. These are the hard physical boundaries we have to work within, no exceptions.
So, we have our goal, that's the cost function, and we have our rules, those are the constraints. We've laid out the problem perfectly in the language of math. Now for the really cool part. Let's see how this all translates into a practical solution using something like Python.
I mean, this is where the rubber meets the road, right? That math formula we just picked apart, it translates almost one-to-one into this clean little function in Python. We're just telling the computer, hey, for any set of power outputs you want to test, here's exactly how to calculate the total cost.
And, of course, we need our rules and code, too. This power balance function here, that directly enforces our supply must equal demand rule. And this bounds variable, that sets the physical min and max limits for each generator. We're basically just teaching the computer the rules of the game. And now, this is where the magic happens. We take our goal, the cost function, we take all our rules, the bounds and the power balance, and we just hand them all over to this incredibly powerful solver function. This single line of code tells the computer, okay, go find the absolute best combination of power outputs that follows all my rules and gives me the lowest possible cost.
And just like that, out pops the answer. To meet 150 megawatt demand, the cheapest possible way is to run generator 1 at 58.33 megawatts, generator 2 at 41.67, and generator 3 at exactly 50. That is the one single optimal dispatch.
And the price tag for that perfect combination? €1,045.83. That is the absolute rock-bottom price to generate that power. The math guarantees it.
Getting this number isn't just about saving a few bucks. It's about making our entire grid more efficient, more reliable, which is honestly such a fascinating field. And hey, if you are interested in the energy market, power system modeling, and you want updates and insights about the global energy market, you should definitely follow the Optatube YouTube channel.
Okay, so we've been deep in the weeds with the math and the code. Let's pull back for a second and think about what this really means for our energy future.
If you take away one thing, let it be this. Economic dispatch is literally the brain of the power grid. It's this non-stop process, constantly solving this incredibly complex puzzle behind the scenes to keep our lights on and our bills as low as possible every moment of every day.
And that leaves us with a really fascinating question to chew on. This whole system we just described, it was built for power plants you can control, right? But what happens when we add more and more renewables like wind and solar, things we can't just turn on and off whenever we want? How does this fundamental optimization puzzle have to shift to handle a future that's way more unpredictable? Now that is the next great puzzle for the grid to solve.